Thank you very much, Kartik, and thank you very much all the organizers for putting together such a wonderful meeting. I think it's wonderful to also honor Professor Yvonne Choquet-Bruard, who has always been a great inspiring person in the field. So I had the privilege to meet her when I was still a graduate student, and so I met her a few times in my life. I mean, other people have met her a longer time ago, but it was always inspiring to talk to her about mathematics, obviously, but also about life and other aspects of society. So I will have a general introduction. I'll say just very briefly a few things about Yvonne Choquet-Bruard, and I want to highlight really her work and how this is very important and continues to be important in nowadays in new research questions in general relativity. I mean, it's overwhelming when you look at Yvonne has done so much in not only GR, but also other aspects of mathematics and physics in general. So it's really interesting to see what she has achieved. Okay, one thing that I would like to do is, as I said, highlight a little bit, let's say, about aspects of her life and work. And I will focus then on her important result, the 1952 well-postness problem for the Einstein equations. And so, of course, because her work is so big and broad, so I'll focus on a certain angle, namely more towards initial value problem and gravitational radiation. And in the second half of the talk, I'll say a few words about gravitational wave memory and some new developments. But first, let me just say a few words here about Yvonne. So Yvonne just was able to celebrate her 100th birthday on the 29th of December. She was born on that day in 23 in Lille as the second of three children. And then the family moved to Paris when Yvonne was 2 years old. So she did a PhD thesis with Andrei Lichnerowitz, and that she finished at the beginning of the 1950s. And actually, the problem she worked on and that the famous 1952 result came out from was a suggestion by Jean Leray, who was a friend and mentor for her for a long time. So one thing that is really striking also when you had the privilege to meet Yvonne is that she really cares about the human being. It's always been important, including her children, her family, but friends, but also if you're a colleague in the field, it's always been important so to put the human being first. So I think this is really amazing. So Yvonne, I'm just highlighting a few things that maybe some of you are very familiar with, some others may not have heard that. So she was a professor for a long time at the Sorbonne in Paris. And in 1979, she became the first woman to be elected to the French Academy of Sciences. In 2003, that's something that Abe also put very nicely. So she got the Danny Heinemann Prize for Mathematical Physics. And in 2015, so that year, she received the so-called Grand Croix de l'Ordre National de la Légion d'Honneur. That's the Grand Cross of the National Order of the Legion of Honor, which is in France the highest recognition you can get. She's also an elected member of the American Academy of Arts and Sciences. And so as these few points already highlight, Yvonne Choquet-Bruard has really paved the way for many women in science and mathematics as one of the first female mathematicians or people working in the fields. So she has always been a really great researcher, teacher, and inspiring person. So that I just wanted to say a few words in that direction. So in the following, I'll take a very slow pace a little bit. And I want to highlight some of her work, or more to say, we have heard about her 1952 result quite a bit. I want to take a little bit a different angle and want to say something, how important that was also for the fact that gravitational waves exist in the nonlinear setting of the Einstein equation. So that was a debate until that proof by Yvonne was done. So as we all know and appreciate, we look at the Einstein equations. I will, for the main part of this talk, discuss the Einstein vacuum equations because I want to talk about gravity itself. But of course, we can couple the Einstein equations to all kinds of interesting matter models. We'll do that at the very end for some type of a neutrino model that we can look at. So here is just a short overview of the classic approach to doing an initial value problem. Because if we want to understand physical phenomena, we want to understand what happens in terms of an initial value problem, right? We look at data that the astronomers give us or data from physics. We set up initial data or a whole class of initial data obeying certain constraints and want to evolve this data under the Einstein equations. From these spacetimes that we create, we want to understand what the dynamics of the gravitational field and answer physical questions. So this is really based on the initial value problem. So let me also put in a little bit of history on the way. So in 29, Darbois noticed that actually general relativity has this constraint equations, namely they looked at the analytic case, so that's an important fact. They didn't look at general functions or data yet, so all of this is in the analytic case, and he recognized, well, yes, we have the constraint equations that we have to solve, and there is what we call here in this notation n, there's a lapse function and a shift vector, ni is the shift vector and capital L n the lapse function. I will change the notation as we go. So this is a lapse function and the ni is the shift vector. So Lichnerowitz then 10 years later, really for the analytic case, looked and actually specified and found and solved the problem in the analytic case for some lapse and shift vector. So yes, we can write these constraints out. I'll write them in a moment, but here is again what we do in the initial value problem, right? So we set up a set of initial data, which is to begin with, if we look at the data, a three-dimensional manifold. I will typically call H in this talk, a Riemannian metric G bar, and a symmetric 2 tensor K, which is going to be the second fundamental form with respect to time. And if we have matter fields on the right-hand side, of course, we have to also specify data for the matter. And all this data has to satisfy the so-called constraint equations. That's already one portion of the Einstein equations, as we know. And then we want to solve the constraint and the evolution problem to solve the full Einstein equations and to create our manifolds, which are the spacetimes with properties from which we hopefully can answer physical questions. So another important thing, so here are the constraint equations, for instance. So they propagate, which was also found by Darbois in the analytic case and then by Choquebriard in general. So first of all, and here we can write the evolution equations typically maybe for G bar and K, but the interesting thing is if you would like, there are different approaches to solving the Einstein equations. You hopefully find a nice hyperbolic equation. You want to derive a hyperbolic set of equations and solve the constraint at the evolution part of the Einstein equations. There are various approaches nowadays how you can do that. So important for us, maybe let's look back at into the year 1952. What were some open questions before this 1952 result? So first of all, as you have heard, and I mentioned or emphasized, all of these results were basically done, the Cauchy problem in the analytic case. So you have really infinite amount of derivatives and analytic functions, but this is really not a physical setting because it does not allow you to talk about causality or propagation of waves. So you don't see any propagation of waves. So that's a very unphysical setting. So it was a great first step mathematically, but physically it does not give you the answers you want. So therefore, the initial value problem in a general physical setting was still open for the nonlinear equations. Another question is causality in the general setting. There were results by Karl Stellmacher from 1938, but he showed uniqueness in principle of solutions, but not existence. So we don't have an existence result. So therefore, one open question was really, do gravitational waves exist in the fully nonlinear theory? And is there a finite speed of propagation of the gravitational field? So with the well-posedness, local existence and uniqueness result of 1952 by Choquebriard, she answered these questions as well. I mean, I'm not mentioning many people who should be mentioned along the way. So there are many people who had partial results, great ideas, and a lot of people really built up the machinery in mathematics to be able for also Yvonne to do that in 52. Okay, so here is the famous well-posted result in one formulation. So let's look at this very briefly. So we have initial data, right? So G bar and K, as given before. And Yvonne introduced the wave gauge, so harmonic coordinates. And under this, so for this data, well, she proved that there exists a space-time which is locally in time, which is a solution of the Einstein vacuum equations, and where H embeds into M as a space-like surface where we get G bar and K to be the first and second fundamental form respectively. And this Lorentzian metric G in wave gauge depends continuously on the initial data. So moreover, its value at the given point P depends only on the past of P. So, and this local solution is indeed unique. So one interesting fact, she wrote this proof for finite differentiability. So she had the initial data in C5, respectively C4. So finite differentiability, that's the big advantage already. Today, we typically use Sobolev spaces. So we put our data into Sobolev spaces, and this guarantees us we don't lose derivatives. But let me maybe just say a few words in addition to what has been said in other talks already, just about this result. So the main issue, maybe if you call it an issue, well, is the class of CK differentiability. So that was the big step forward because we don't have analytic functions, but finite differentiability. So we can see the propagation of the field and gravitational waves. Nowadays, so the solution to not losing, let's say, derivatives is really using Sobolev spaces. So that's what we do nowadays. So other people like Schauder, Lorez, Sobolev, etc., then really improved these results. Also Yvonne, there's many interesting follow-up results. But maybe just one more word about the proof. We have heard already, yes, she used harmonic coordinates, or we call them also wave coordinates. And in these coordinates, the Einstein equations become really interesting. So, and in these wave coordinates, we really have a hyperbolic system of equations, which, well, are quasi-linear, and we can really solve these equations much more nicely. So we have a quasi-linear system of wave equations. That was one big, let's say, step in the proof that she was able to derive these equations. She solved these equations. In fact, she had a more general set of systems she looked at, and the type that applies to GR is then what we are interested in here. So I'm not going to go deeper into this, but just say a few words about in view of gravitational waves. So if you remember from history, in 1916 and 18, Albert Einstein found in a linearized setting, he linearized the Einstein equations. He found wave solutions of his equations. But he knew, of course, if he linearizes the system, so he might have either this might be artifacts of the linearization, or it's not clear if the fully nonlinear theory also admits for wave solutions. So he kind of went back and forth, believing, yes, the fully nonlinear theory has wave solutions or not. So this was an open, burning question. Does the fully nonlinear Einstein equations have gravitational wave solutions? And as a result of the 52 Choquet-Briard local existence and uniqueness theorem, she proved with that result, yes, gravitational waves exist for the nonlinear Einstein equations, and they do propagate at the speed of light. So we have a finite propagation of the gravitational field. So she really resolved the confusion that was around. So there was a lot of confusion in the field up to that proof about gravitational waves. So I'm focusing a little bit on these aspects of her result now. So if you want to go on, there, of course, there's been many works important for gravitational radiation nowadays. I'm just citing a few, and many more people contributed here. So there's the whole work by Bondi, Pirani, Trautmann, Robinson, Sachs, etc., van der Burg, and many other people that paved the way also in the 1950s and 60s. And also, let me maybe mention one or two other things: Choquet-Briard, Müller-Zumhagen, and Seifert, but then also Alan Randall. So they looked in the 60s and 70s, and Alan Randall in 1990 at the characteristic initial value problems, which was really solved then by Alan Randall in 1990, which these questions became also important for many works nowadays, like, for instance, black hole formation by Christodoulou in the 2008 and other properties. So this is just highlights, but we want to focus in this talk more on gravitational radiation. So what are these? I mean, many people in the audience are experts. I'm not going to go too deep, but I would also like to say a few words for maybe the students in the audience. So we can think of these as really ripples in space-time. You can think of them as fluctuations of the metric. I prefer to talk about the curvature, the Riemannian respectively, Weyl curvature in the Einstein vacuum case. So if you think about our space-time and you have the curvature that comes out in our space-time, so we have fluctuations of the curvature of the space-times. There's a pulse of these fluctuations traveling at the speed of light along null hypersurface. So we may have a source going along its time-like curves, like a boundary black hole merger, for instance, and they send out gravitational waves, and we are far away from the source, so we can ideally place ourselves at future null infinity, for instance, and we observe this gravitational wave. So we want to understand what's coming out, for instance, of an initial value problem for typical sources, and we want to then go out in the solution space-times and read off from future null infinity what the radiation looks like. So, of course, we live in a really interesting era, I mean, mathematically and physically. Mathematically, many interesting tools are available to study deeper Einstein equations than they were maybe 50 or 60 years ago. From the experimental side, it's really interesting. In 2015, LIGO detected for the first time gravitational waves from a binary black hole merger, and several times since then. And we've had the LIGO-Virgo collaboration and more, hopefully, being on board in the future. So they have the LIGO-Virgo collaboration detected for the first time waves, gravitational waves from a binary neutron star merger in 2017. And at the same time, several telescopes were able to register data from that merger. So we expect many more interesting results to come. And I think this is really the beginning of a new era, because not only do we have telescopes, but we have now gravitational waves that tell us more about the universe, which is a completely different type of data that we haven't had access to before. So one more time, so the 52 result by Jauquier-Brouillard. So not only did she write down the Einstein equation as a quasi-linear wave equation, and solve the Cauchy problem for these equations, but she also showed that we do have gravitational waves in a physically meaningful setting, in a physical setting, and we have finite propagation for these waves. So nowadays, using energy estimates and more modern methods, we use Sobolev spaces, etc. But all we do, if it's a local or a global result, still remains built on either directly her work or modification of this work, even nowadays when we talk about such questions in GR. So, as I said, Yvonne looked at the general set of equations. Maybe for the sake of time, jumping a little bit forward. So she looked actually at the more general set of hyperbolic partial differential equations, and GR was a subset of these equations. But I'm maybe jumping here to a little bit forward. So together with Bock-Gerach, she had in 1969 another important breakthrough result, namely they showed that there exists under these assumptions that there exists a unique globally hyperbolic maximal development of these space-times. And of course, the next question to ask is, well, what about this development? Does it actually is it going to be geodesically complete, or are they black holes or singularities? And that one of these questions was answered in a fully general nonlinear setting in 1991 by Dmitry Christodoulou and Sergio Kleinerman, showing the Minkowski stability in the fully nonlinear case. So you take a set of data, initial data, where you have, these are asymptotically flat initial data, which are small in the terms of weighted Sobolev spaces. And then they showed that you have global solutions, which again tend to asymptotically flat spacetimes, which are globally causally geodesically complete. So no singularities, no black holes form. So there were generalizations of this result in many directions. And I just want to mention the two types of initial data that will be important. So Christodoulou Kleinerman looked at initial data where if you go to space-like infinity, you can represent this data as this metric, G bar, especially this 2m over r, m denotes the mass here. And you have a tail term which decays like r to the minus 3/2. And k decays toward according to this law. So in my generalization, I'll look at spacetimes that decay like just delta ij and r to the minus 1/2 at space like infinity, and corresponding less decay for r to minus 3/2. So these were results for small data, but we are going to be interested in large data. So maybe one more thing, I'll look at classes. I call them B. D is what Christodoulou-Kleinemann found. Classes B are spacetimes coming out of this data when you solve the Einstein equations. And maybe we just concentrate on A. So if you go back, if you replace the little o here with big O, then I call this class capital A. So we will look at these types of data in what follows. So one more thing, I'm interested in large data, but I mean, of course, there could be black holes or singularities around. So the interesting thing of these geometric analytic proofs of Christodoulou-Kleinemann, but also in my generalization, is that, well, the smallest assumption was used to guarantee existence of the solutions, but you also have a very precise quantitative description of how the fields behave towards null infinity along null hypersurfaces. And that part is basically independent from the smallness assumption. So even if you have large data even in the initial data, so we can still find a sufficiently large part outside of a compact set that behaves as that has a complete future, that has reaches future null infinity. And so we have a complete description of the field outside of such compact set, how the field decays along null hypersurfaces, and how this field reaches future null infinity. So we can make sense of large data that decays according to these initial data sets. So we can make sense of large data within this realm. Okay, having said that, I'm going to use some foliation of our spacetime, of course, with some time function t, but also null hypersurfaces are going to be, let's say you have null hypersurfaces labeled by a function u, which is first of all a solution of the Eikenel equation. So cu in the outgoing direction will be outgoing null hypersurfaces. Having said that, let me also introduce a little bit more about the foliation. So if I'm sitting here on a space like S, space like 2 surface S, then in the outward going direction, I'll look at some vector, let's say vector field called L, generating null vector field of outgoing null geodesics, and the ingoing vector field is called L bar, L or E4 or L bar or E3, and G of L bar is equals to -2. So I have null directions, L and L bar, that I can call E4 and E3, and I'll complement this frame with a local orthonormal frame tangential to this surfaces S. So I'll have this null frame with respect to which I will decompose the quantities, which are the curvature and the other quantities. So for gravitational radiation, one of the important quantities are the shears. So we'll look at the curvature components in a moment. But if I now sit on one point here on such a surface S, I take the second fundamental form with respect to the outgoing and incoming null vector field. So with respect to the outgoing vector at this point, so the second fundamental form is called chi. With respect to the incoming, I'll call it chi bar. So if I look at the traceless parts, this is giving me the shears chi hat outgoing, chi hat bar incoming. So these are going to be really important elements talking about gravitational radiation. And if I look at the traces of the two, we have the expansion scalars. Okay, so this will be coming up in the second half of the talk. Also, just to mention that, so maybe don't learn by heart all that's here, but I can take my Weil curvature, which is the same as the Riemannian, obviously in the Einstein vacuum case. So the Weil curvature components, I contract them twice, for instance, with the incoming 3 direction, like here, and then project them tangentially on this surface. So I get all kinds of different components of the Weil curvature with respect to that foliation. And maybe more interesting for you is how they decay, and not so much how I call them. So tau minus in this notation, you can think of u, that's tau minus squared is 1 plus u squared. U is really the retarded time, if you want to think of it that way. or which gives us as a solution of the Eikenall equation, giving us the foliation into null hypersurfaces. But at null infinity, we think of this at the retarded time. So the leading order curvature component written that way, if you look at Kristallop-Kleinemann spacetime, so this will decay like an r to the -1 and u to the -5/2, especially specifically. So in classes of this data, you get spacetimes where the curvature components decay and peel like that. So the one to remember, certainly alpha bar, the rest you don't need to remember at this time. If you have this very slowly decaying spacetimes, obviously you don't get that much decay out because the initial data to begin with has not so much decay. So you get the leading order curvature term decays like r to the -1 and some u decay. Then the next one is r to the -2 and some u decay, and the rest is kind of swallowed in this very slow decay. So however, there's a little bit more to say about these spacetimes. I want to look at data that come out of this speed type, but for large data now, not confined to smallest assumptions. So maybe I can jump a little bit through the next slides, but just to tell you a few things. Now, if you solve the Einstein equations and you see, well, how do the curvature and the other types of geometric objects decay. The other thing, maybe only two things are to remember. The chi-hat in this very slowly decaying spacetimes only has a decay of r to the -3/2. And the chi-hat bar, like r to the -1, u to the -1/2. Maybe the rest we don't need to remember, but we can get out all these different decay behaviors. I'll also jump maybe just to this equation, and there's nothing to remember here, but just to tell you, we'll use the Bianchi equation in the future to derive some results about Einstein equations. Here on the left-hand side, we have curvature components rho, and some curvature and geometric components on the right-hand side that we will analyze later on. But rho and sigma are two specific curvature components that we shall talk about a little bit more in the future. So anyway, if you look at this very slow decaying spacetime, so one problem, if you look at that, you may say, well, many of these elements, geometric quantities, but also curvature, do not have limits at null infinity. So that looks like a problem. So yes and no, but let's look at the chi-hat. So the shear with respect to the outgoing null hypersurfaces that only decays like r to the -3/2 in this type of setting. So if you look at that r to the -3/2 itself, the chi-hat does not have a limit itself, but it's not so bad because we can look at the following setting. Let's sit on one of these space-like surfaces within one outgoing null hypersurface, call that Cu, and we look at a specific point on one spherical section here on Cu, and then we look at the nearby outgoing null hypersurface Cu0. We have two Cu and Cu0, two nearby null hypersurfaces and the corresponding sections Su, Su0. And I look at the specific point here and take the difference of these values of chi-hat, r squared times chi-hat at such neighboring points. So this is a finite value, and even if I go out to null infinity, the difference remains finite. So the difference of two such points going out along null hypersurfaces has a limit, which is this object here, namely d3. This is the derivative of chi-hat into the null direction L bar, or E3, the incoming null direction, projected onto the surfaces S. So I now take the derivative with respect to 3, but integrate this with respect to the retarded time u prime. I call it here from u0 to u. So this is the limit that this difference goes to. So with other words, we see that there is a dynamical part lying beneath the leading order diverging term is non-dynamical. So let's take that away. We find the next order term is dynamical and well-behaved. So we'll actually look at these terms. Something similar happens with the non-peeling curvature components, and we can look at the dynamical pieces beneath that. So that's one thing that happens here. Is there a question? I think
I have a question.
raised
Can you hear me?
Yeah, Abe, yeah.
So about in this class of spacetimes you're looking at. I think it's class B that you're looking at right now, right?
Right.
Yeah. So in that case, the component which normally falls like 1 upon r cube, which has information about Bondi mass, is
Right.
falling like only r to the minus 5 half.
Exactly.
Right? Yeah. So therefore, even though, as you are just explaining, the news might still have a good limit,
Yes.
but still this component, which the Coulombic component, which is, people call it real part of cycle naught. I forgot now what you call it.
Right, right, that's fine. Yeah.
That component would not have limit, right?
Right, that's an interesting point. That's, some of the next remarks I'm going to focus on. Exactly, the rho itself does not have a limit at leading order, just r to the minus 5 halves. But this is a non-dynamical part. So if I take that off, I will get a good limit for rho. So that's going to be a main point in the next few slides. Exactly.
Right.
There's still
exactly.
something.
But still, the Bondi mass has rho in it. I mean,
Bondi mass is going to be fine, actually.
Yep.
Right. So the Bondi news is going to be fine, and the Bondi mass is also fine, actually. So there are some relations that you will see certain things will cancel out, but what we would like to have out there is still well behaved. So we can still extract something about the Bondi news and mass and the gravitational radiation from there.
Okay. Thank you.
Thank you. Okay, so here is something just related to what Abed just asked. So some curvature components have a limit at null infinity. Others, the leading order does not have a limit, but we have to look underneath the leading order for these other components. So the leading order curvature component alpha bar has a limit. If I multiply this by r, I call this double A. Or A, the W means just wild curvature. I may omit that in the future. So it's just a capital A. And the beta bar term has a limit, which I call beta bar underline, or beta bar. So, and these objects then have some decay, as they decay also for large U in the sense that this decays according to u to the minus 3 halves or u to the minus 1 half. I also have limits for certain important, let's say, equations at infinity. So from local equations, we derive these limits. Namely, if I take a u derivative of this limit psi, you see the other one of the shears, the chi-hat bar, multiplied by r. This does take a limit I call psi. The other shear does not. So I have a limiting equations between derivatives of with respect to u of this psi, which gives me the leading order curvature component, and also divergence of psi is equal to this beta bar modulo some constant. So there's some other relations we will use, but these are some of those. Now let's look at what is this. So if I will show you that in details, but rho 3 means I take the rho component that Abe pointed out from before, which only goes like r to the minus 5 halves. But if I take of this rho component a derivative, this little 3 means I take a derivative with respect to the ingoing E3 L bar null direction, and I'll project things onto these spheres. So this is a derivative into the 3 direction of rho, and sigma so is another component. Here I'll mention in a moment. So there will be, so we have these components, that's a derivative into the 3 direction. And we'll see from the Bianchi equations in a moment that there will be some other terms on the left-hand side of this equation. So certain things for large data may not behave well enough, but they will cancel out. On the right-hand side, we know that we have well-behaved data. Some of these come from the rho curvature component, some others from, we'll see, other components in the Bianchi equation. So nevertheless, what this theorem tells us, the shortcut is on the right-hand side of this equation, all of these components have well-behaved limits. So I multiply with r to the 3, the right-hand side, each component that will show up in the next equations, multiplied by r to the 3 has a limit at future null infinity. Therefore, also the left-hand side here has a limit that we can deal with. And now we have to make sense, what are really these structures, what are these components? That will be part of the next few slides. But before I go, I will derive this from the Bianchi equations for you. But before we go there, I would like to say maybe a few more words again about gravitational radiation, where we are going. So remember, LIGO measures the motion of nearby test masses or geodesics, right? So test masses are like mirrors suspended by pendulums like here. So we can describe them on Earth by the Jacobi equation, so really marking nearby geodesics. And when a wave comes through, we have curvature, and this changes the places of these test masses and the light that we send back and forth to measure the laser light to measure the distances. So for a fraction of a second, when a pulse comes, we see change of these geodesics or the test masses, which has been recorded by LIGO already. They got the Nobel Prize for this. And so Ray Weiss, Barry Babbage, and Kip Thorne got the Nobel Prize, standing for many hundreds and thousands of people that worked on LIGO. What we see here, you can think of that. We can describe this by the Jacobi equation, where on the left-hand side we have an acceleration, right, of nearby geodesics. And on the right-hand side we have a curvature term. So basically we integrate twice this this equation to get some displacement, and we have to understand the right-hand side. So what LIGO has already many times recorded are these instantaneous displacements. When the gravitational wave train is coming through, these geodesics will move and we will follow in LIGO what happens. But there is something else that has been predicted in GR but not yet observed. And we hope that LIGO and some other instruments will see that in the near future. What is that? It's predicted that when the wave train goes through, after that, the test masses will go back to rest. That was known before, but they will be displaced. Like these arrows, of course, are too big, but they will be displaced permanently from their original position. They will not go back to rest where they were before the wave train came through, but there's a permanent change of this that we call memory effect. So this is, in fact, a memory. So there are two types, at least at leading order, of memory that have been known. So let me say just a few words. One effect was that we call nowadays the ordinary memory effect, was found by Yakov Seldovich and Alexander Ponyarov in 1974. They looked at the linearized Einstein equations and found that there is such a remaining displacement. There is another effect that we call null memory effect, which was found by Dmitry Christodoulou in 1991. And he looked at the fully nonlinear Einstein equation and found actually a second effect. He rediscovered, if you want, the ordinary effect by Seldovich and Ponyarov. So he mentions that was known already. But he found a second effect, which is different, which we call the null effect, and which is supposed to be really large for binary black hole mergers, for instance. There has been a lot of work, early works on memory in GR by Damour, Blanchet, and many other people like here. There's also related early works, I mean, in the GR setting, but also for infrared problems in quantum field theory. And Abeash Dekar, who is here, which is great, and he and also collaborators in the 70s and 80s have done a lot of work on asymptotic symmetries in GR and also quantum field theory. Let me also mention a more recent paper by Lasky, Thrain, Levin, Blackman, and Chen. So they suggest that we should, stack gravitational, let's say stack events like binary black hole merger to finally detect gravitational wave memory with LIGO. So there's a lot more, and I apologize if I can't mention everybody. There's a huge growing field talking about memory and analogs. Maybe just a few things. Of course, when you couple Einstein's equation to other fields like electromagnetic fields, we also found a memory with Chen and Yao, for instance, coming from the electromagnetic field, a contribution to the Christodoulou or the null memory in that case. So there's other fields coupled to Einstein equations generate another null memory. So with Garfinkel, we found more than 10 years ago, 2012 and 13, electromagnetic memory effect, which we found these two analogs of ordinary and null, also for the pure Maxwell equation. So no GR, for instance, involved. So a big open question is what happens still in quantum fields, etc., for these fields. There's a large group of people that have been working on these. So apology again for people if I didn't mention anybody. There's a lot of people who should be mentioned. It's a huge growing field and really interesting questions. So let's go back to the setup of LIGO. Remember, the geodesic, the nearby geodesics are marked by test masses. And these test masses, we can write down the Jacobi equation here on Earth. So we have on the left-hand side of the Jacobi equation an acceleration, and on the right-hand side, the curvature term. So if we integrate twice, we can get a displacement, right? And on the right-hand side, integrating the curvature term, we want to use for what is on the right-hand side a little bit more insight. If we integrate it twice, we can derive an equation of that sort. What do I have here in 35? So what I call here a permanent displacement, that's a delta x on the left-hand side. So this is given by d0 is just some initial distance between test masses. R is the distance from the source to the detector. We want to sit at the detector now. So this chi minus minus chi plus, this is something I'm going to introduce, but this is a geometric quantity, has to do with the shear limit chi hat that I mentioned before, or better to say the derivative of that and integrate it over retarded time u at null infinity. So if we integrate twice the right-hand side of the Jacobi equation, so from the curvature term, we can derive some geometric quantity I call here chi, and we would like to understand what is that right-hand side and derive what's behind this. So if we have asymptotically flat system where you have anything which decays like mass over R, even if you have a non-homogeneous setting, just something which is homogeneous of degree -1, then their ordinary memory is sourced by a change in the radial component of an electric part of the Wild tensor, the rho that we had seen before. And the null memory is sourced by energy radiated away by the waves themselves. So that's the chi hat bar squared, the bond in use integrated. And in the new situation of very slow decay, there's a lot more. So we don't only have ordinary memory by electric part, but there's also magnetic part showing up. Contributing to the ordinary memory. And not only that, both the ordinary memory from the magnetic and the electric part diverge at the rate square root of retarded time u. There's a lot of other additional structures that I would like to derive these in the remaining time of this talk. So before we go there, for the people in the audience who have maybe not heard so much about these questions, we can decompose the Wild tensor into so-called electric and magnetic parts. And this is the decomposition. So T is just my time coordinate. So if I look at the general Wild curvature, I look at these components, A and B are just spatial coordinates here. Indices. So then the EIB, this is what we call the electric part of the Wild tensor, and correspondingly here, the next line, if we do look this with the spatial volume element, so the HAB defined this way is the magnetic part. This is a nice analogy to Maxwell equations, but we call this portion the electric and this portion the magnetic part of the Wild curvature. So in this decomposition, the NN component, so if you look at a space like 2-sphere again, but I now take a normal that is tangential to some space-like foliation. So I would call this NN component rho from before. That's the electric portion of one electric component of the electric Wild component, and HNN is one specific magnetic component of the Wild tensor. 38 is just one specific way of writing down this Jacobi equation that I mentioned. So this delta x is just a displacement, right? So if I have two derivatives, I get an acceleration here on the left-hand side. And on the right-hand side, we have just these components here of the Wild tensor sitting there. So if I integrate twice this equation, I get a displacement that we will look at for LIGO. Okay, rho and sigma are curvature components I would like you to keep in mind. So what I mentioned before, if we have anything that decays like 1 over R or homogeneous of degree -1 mass over R, we only have the electric parity memory and everything is finite. No magnetic memory occurs at all for asymptotically flat systems of that type. Now, if we go just a little bit below R to the -1 decay, even an epsilon, but you can go all the way further, then we have magnetic memory suddenly occurs. There's a whole new panorama of new memory that shows up. Okay, maybe briefly, there have been some kind of unusual examples put forward by Gautam Satischandran and Bob Wald, but also by Thomas Miller and Jeff Winnicore in the past. Namely, if you do a very strange stress energy of an expanding shell, if you put this into a linearized gravity setting, you find something like ordinary memory. Or with Madler and Winokur, they looked at some source-free homogeneous special case of incoming gravitational waves, also in a linearized setting. So basically, you put in magnetic memory at past null infinity, then you will also get it at future null infinity. But what is new in the results I'm discussing here, so we don't put in anything initially. There's nothing initially put in the initial data. So the evolution actually picks up this magnetic memory. That's in the pure Einstein vacuum equation already. We find this magnetic part of memory for the slow decay space-times, but also some other results are found which are different here, and memory grows in retarded time u. All right, so let's look at the following. So just to maybe a few more minutes to show you how these results come about. This chi minus minus chi plus, remember, that's the right-hand side that comes out from the Jacobi equation once we integrate twice. That gives us a permanent displacement in LIGO. So it includes what the following will show. This will include electric part of curvature, that's always there, but it will now also include for the new very slow decay spacetimes, magnetic part of curvature. So in order to find these, we have to first of all look at the Bianchi equations and then solve a system for this chi minus minus chi plus at infinity, some Hodge system at infinity that we can derive the solution from. So let's look first at the electric part, and that's the rho component, Abe, that you asked me about. So let's look at the Bianchi equation for this. So 3 means just I take a derivative into the L bar incoming null direction. The slash means I project things tangential to the spheres. So if I have a rho index 3, this is just that portion. So the Bianchi equations look like that. On the left-hand side, I have this rho component, right? So that gives me that generally, if you have a lot of decays like r to the minus 3, but the leading order component of rho here does not. But I take the 3 derivative, and then I look at the right-hand side. So we will see epsilon and theta, these are Ricci coefficients, so that's the torsion, beta bar is another curvature component. So all of these terms on the right-hand side, the last 2 terms, they decay fast enough so that they will not contribute to a limit when multiplied by r to the 3. So, but the divergence of beta bar is actually nicely decaying, but this chi hat times alpha bar has a bad decay. So we can do some computation here, take into account some relations between the shears and the curvature. So we can compute from that one term 2 more terms. So we have lower order terms that we can ignore at the moment, but we have this term that shows up, the trace chi times chi hat bar squared, which is good in terms of r to the minus 3. So this one decays nicely. So we can put that, this is fine. But then we have this term, which still decays like r to the minus 5 halves. This is the chi hat dot chi hat bar, and we take a ddu of that. So let us do the following. Let's throw that term on the left-hand side and look at equation 40. In 40, the left-hand side has these terms, rho 3 and ddu of these shear terms. But the right-hand side is something that decays nicely. So let us make a distinction between small and large data. For small data, the rho 3 itself is controlled, and also the other term, the shear term here, the derivative of that, is all of these terms are by themselves well-defined at null infinity. However, for large data on the left-hand side, there might be terms in rho 3 and also the other one that decay like r to the minus 5 halves and some bad u behavior. However, because we know even for large data, right-hand side here is controlled, so these terms will cancel out on the left-hand side. So whatever contribution, we can now go deeper into the analysis underneath the non-dynamical bad term in rho. So when we take derivative like that, so the left-hand side is well defined and has now a limit at future null infinity. So let's look at that. So what we will do is we multiply this equation by r to the 3 and take a limit to future null infinity. So now the left-hand side of this equation, I will give it a name in the limit. So I look at the left-hand side of this equation, multiply by r to the 3, and take the limit to null infinity. That is well behaved. I call this P3. And in the future, in the next minute or so, we'll also integrate this with respect to retarded time u. Of course, I have an additive function here which is a constant in u, but this function will disappear when I integrate in u later on. When I take an integral of this term. So, I mean, taking the limit, so we get on the right-hand side, everything is well defined. So I take the limit of this equation, P3 is the left-hand side. The right-hand side itself, all is well defined. This takes limit at future null infinity. Now, I have to jump a little bit forward. So we can show that there are all these structures and some behavior in retarded time u, which is interesting. But let me also take a limit of this object. Remember, chi hat itself had a very bad behavior, but I take the u derivative of chi hat, and this has a good behavior. I take r squared times d du of chi hat and take the limit at null infinity. I call this chi3. If I integrate that, that's going to be what I call chi. So from other relations that we can show that at null infinity, I have these relations between psi and beta bar, but also between chi3, this new term, and the psi. So with other words, from the equation before, I have this P3 left-hand side, which is now given by two divergences of this chi3 object plus psi squared. So I integrate that. I get an integral, which is the following. I get the double divergence of this chi object. I take limits for u to plus and minus infinity. The other hand side is given by P itself, the difference P minus minus P plus, and the bond in u is integrated over u. So this is giving me what we call, this will be giving us what we call the electric part of the memory. So let me also derive just briefly the magnetic part. So we look at the Bianchi equations. That's taking just the last few minutes of my talk. So the Bianchi equation for the magnetic part of the memory. So again, the D3 derivative, we look at that. We have lower order terms that we throw away. And again, number 50 here is the Bianchi equation for the magnetic part. With one at the level of one derivative into L bar direction. And again, we look at the chi bar times the Hodge dual of alpha bar. And we can say, well, we also do a computation and we get 51. So the chi hat, wedge chi hat bar is also not behaving nicely. I put it on the left-hand side of the equation. And the right-hand side, the curl beta bar is actually, we know we control that at the level r to the minus 3. So again, we do something similar like before. The left-hand side in total has a net decay like r to the minus 3. So we can multiply this equation by r to the 3 and take its limit towards future null infinity. The same as before. So we do that with the left-hand side in equation 52. Take the limit at future null infinity. And again, we will integrate this term with respect to retarded time in what comes and do the same thing as before. So if we look at this equation, the limiting equation is then that Q3 limiting term from the left-hand side and only a curl beta bar, B bar on the right-hand side. So again, we can integrate this equation and we obtain 57, which is a curl of the divergence of these chi differences. And we have a Q on the left-hand side. So these are differences when u goes to minus respectively plus infinity. Now, there's an interesting thing. So this magnetic term would not be there at all if we had spacetimes which decay like anything like 1 over r or any mass over r term. This would all be identically 0. They only start appearing if I go just an epsilon below 1 over r decay, so worse. So what I mean by this is the following. Let's look at this Q components on the left-hand side. So for instance, I can look at Q at U0 just sitting at the fixed S2, at the fixed U0, look at one of the spheres S2, and then when I look at this component Q U0, I let U go to infinity. Let me keep U0 fixed, and then I'll let U go to plus or minus infinity, and then this difference between Q of U and U0 is no longer finite. This difference, in fact, grows with retarded time square root in this case. So maybe one last thing to summarize that. So what I want to show you, this difference chi minus minus chi plus, the divergence, I can compute that in detail. So I can there exist functions phi and psi which obey this equation. So I want to replace my divergence of the difference of the chi's by some theta. So this theta is that. So then I can apply nice Hodge theory on these surfaces, telling me that the divergence of C is equal to the Laplacian of phi, and the curl of C is equal to the Laplacian of this function psi. So I have these equations 59 to 61. So I know that the divergence, the theta, obeys this equation. If I take the curl, I have equation 60. If I take the divergence, I have equation 61. Again, equation 61 is always there for r to the minus 1 decay. So that's the P is giving us the electric part of memory. F is giving us the null contribution of memory. And the Q here is the magnetic portion of the memory, and that would be completely zero if we have faster decay. But it's not zero, and there's a lot of interesting new structures if we have very slow decay. So in other words, I'm wrapping up my talk here. What is new, basically, or in the last few years, we have magnetic memory, which is growing like square root of retarded time u. So we are able to look underneath the actually bad behavior of the rho and sigma terms, which actually don't have a limit, but the next order terms are dynamical and have limits which we can explore. We also find that electric parity memory is growing. So the interesting thing is that as soon as you go a little bit under worse than 1 over r decay, all these new memories show up. There's a whole new panorama of new structures which show. We can do the same thing if you plug in null fluids, for instance. Think of neutrinos. They are very light. They have a very small mass, so we can model them by some null fluid. And if we do that, we actually get some interesting results. Namely, if we put in a null fluid on the right-hand side, the geometric terms have the same growth rate like in what I showed you in the Einstein vacuum case. The new terms for the null fluid plugged in, they will be growing at some square root of retarded time u. So interesting for us, there's actually, if you have null fluid, there's an electric memory growing at square root of u coming from the stress energy tensor, a new term, which adds to the null memory. And there is, if we have big O, and actually if we have big O of r to the minus 1/2 and even worse decay, then a new memory shows up from the stress energy, which is magnetic. So that's a curl of T in the magnetic portion. So there's all this new structure that also shows up. So here's just a summary of that, which we had gone through. There are all these new terms showing up. Specifically, we have magnetic memory intrinsic in the Einstein vacuum and null fluid case. They grow with square root of u, or correspondingly u to the plus alpha if you have different decay behaviors initially that you assume on your data. So maybe just very briefly, so I also want to focus, maybe just mention one result with Polnareff. We found some nice, interesting memory lately. So I told you, right, the test masses will go to rest for binary black hole mergers after some time, but we looked at the completely different scenario. So for instance, a supermassive black hole surrounded by a large, very large accretion disk, and you let a very small black hole go through the plane of the disk, orthogonally intersecting it. So that's an interesting scenario because it gives us a jump in the acceleration of the small black hole, which results in a jump of the curvature of the space-time. So that is a pulse which will arrive at our detectors, a very short pulse, but this pulse will actually be around, or the velocity of the test masses will actually be non-zero for a very long time. So for a very long time, let's call it delta U, this will create a velocity-coded memory. So instead of going back to rest for the test masses after just a very short time, this is a scenario for a long time, sometimes like around a year or so. For some examples, we find a velocity-coded memory. Maybe I have to wrap up. So one other thing is that we also found with Garfinkel, we suggested, by the way, for this electromagnetic memory, not in GR, we suggested a way to detect that with antennas and a short pulse. So maybe I'm not going here, but just thank you very much for your attention and leave the floor open for questions.
Thank you, Lydia, for the wonderful talk. If you have questions, please raise your hand. Sumati, go ahead.
Yeah.
Oh, you were clapping, not raising hands.
Thank
Gautam
you.
has a question.
Yeah, please, can you ask you? Yeah, go ahead with your question.
Hi, Lydia. Thanks for the talk. Can you hear me?
Yes, hi. Yeah,
Yes.
thank you.
So you mentioned the result with the null fluid, and it went by a little quickly. What physical situation did you have in mind? You mentioned neutrinos, but I didn't. So what kind of scenario were you thinking where that would give you such slow decay?
Okay, yeah, a good question. So I thought of, for instance, so if you think of any kind of object other than, let's say, maybe if you look at what we have looked at, binary black hole mergers, etc. So if you look at that not embedded into huge clouds, etc., then we would treat them like a 1/r decay system. But so, for instance, you could think of maybe neutron star mergers or something, black hole mergers in huge neutrino clouds, or for instance, dark matter, light dark matter around galaxies. So what I have in mind with neutrinos, for instance, they are, of course not, they have a very small mass. So if they go at the very high speed, we can treat them like a null fluid. This is older work with Bob Wald and Garfinkel and other people that we showed. If you have very fast accelerated particles, they will pick up the null memory. So you don't have to have a null mass, but you can model a neutrino, first of all, by some null fluid. But there could be some huge neutrino clouds, for instance, around the source, right? And another way of looking at that, so we have some neutrino halos around sources of gravitational waves. So that would mean you cannot treat them like a 1/r system, but something different. And also something that I got interested in lately is if you look at huge halos of dark matter around galaxies. So now there has been a trend in astronomy, as far as I understand, that people think this is maybe not all cold dark matter, but maybe warm or even wave-like dark matter could be out there. So they could, I mean, still form halos of a huge extent. And then you would have to look at decay rates, which are different, and that would be conformed with some of the decay rates I've shown here.
Okay, thank you.
Yeah, thank you. Abe, maybe you have a question?
Yeah, so this is about this large data that you sort of mentioned early on in the middle of the talk, basically. And
yeah.
that was a very nice clarification that although in this various stability of Minkowski space analysis, one assumes small data for global existence and uniqueness. But in fact, as you're saying, that if you're just interested in some two retarded instants of time, and so you can look at the initial data and its restriction to compact part of the Cauchy surface, that could be very large. But
right.
Can you tell a little bit more about how large, for example, I mean, if it is just arbitrary, then, are you saying that in fact, naked singularities never form? So I would like to understand a little bit more about what class of large data one is considering.
Right, so that is up to you in the end. So what I did here is just, I mean, look at, as you said, right? So I look at out of a compact set, etc. See, I do get prescriptive, I mean, I do get data at null infinity. And then what you can say, well, you could exclude, for instance, you could exclude initially, for instance, that you exclude naked singularities in some sense, or you in other questions, you could allow certain things to form. But that is really then, you can gauge the system a little bit, right? So it depends there's a very large setting I kind of presented here. So you can ask more precise questions within that and put that into your data and let it evolve and see what you can get out of this on the evolution along null hypersurfaces, for instance. So there are two things. One is more or less a method how to treat that, but also results presented here in the sense, yes, you do have a portion of future null infinity where you can read off all these questions, but then the question, these answers to these questions. But in principle, you can also modify the data, right? So in that set, if you're interested in a particular question, you can modify the data and solve the equations like this and see what different results you get there. So in principle, you. Mm-hmm.
So I mean, but I'm still very puzzled by that. So you're saying that
okay, which part?
I could give myself a compact support on a Cauchy surface, arbitrary. I mean, smooth maybe. I mean, some differentiability class, but arbitrary large.
Sure.
But arbitrary large data, and still I will get some, this between two null hypersurfaces.
Mm-hmm.
Geometry will be perfectly well defined all the way to infinity, and
right.
And anything like caustics or I don't know, or some naked singularity would not form. Is that what you're saying? In
right.
that region?
Yes, I'm saying that if you're far enough from the compact part that I'm cutting out. Yes, that's what I'm saying.
You're far away, far enough in the retarded time.
Yes, in retarded time, exactly. So you can still show that you can get out to null infinity if you look at it that way.
I see. So, but this is very nice. I mean, in some sense, there is a version of cosmic censorship here, right? I mean, saying, I mean, partial in the sense it's not all for all time, but for some
Not for all
finite
time.
amount of time, you're saying that the cosmics, I mean, the naked singularities don't form.
Right, and of course you assume something on your data, you have some differentiability, etc., but you don't assume it to be small.
differentiability, right? Yeah. So okay, so that I think could be emphasized, because that is, I think, a lot of people think about naked singularities, and so this is a very nice result, which says that at least in this finite instance of time, between the finite instance of retarded times, in those patches of space time, there are no naked singularities. That's what is being said, right? Thank you.
Yeah, thank you. Yeah,
Sucheta, go ahead.
Yeah, thanks for the nice talk. I was wondering, so since you started from the initial value problem to derive these different memory effects, there's nothing stopping you from doing this in dimensions other than 4, right? Let's say I do in 3 dimensions electromagnetism. Do you know of any analog of these different memories? I mean, gravity.
There have been all kinds of extensions by, I mean, also, I think even Gautam, maybe you have worked on that, Bob Wald and other people. There's a lot of people who have looked at this, and then you look at even an odd spatial dimension. So there have been all kinds of generalizations of memory to higher dimensions, exactly, yeah. Analogs or memory in these dimensions.
Maybe we can have one more quick question if anybody wants to ask.
I just wanted to make one comment since nobody's asking questions. This is really related to Lydia's early remark about how Madame Choquet's work was seminal in saying that there's actually causal propagation, right? But I mean, Madame Choquet herself apparently did not think of this as establishing gravitational waves, because in this 2015 Einstein Centennial Conference, the Conference of Centennial of General Relativity, she asked the question, right? What is a gravitational wave? And I thought it was so cute that she asked this question of all people, because she's the one who pioneered this work. But to her, I mean, she was genuinely saying that what we mean by gravitational wave is not clear in a finite compact region of space-time. One really has to go to infinity. So I had a very nice discussion about it. And so I just wanted to pass on that as a very interesting remark.
Yeah, thank you, Abe. Yeah, it's always, how do you define things? But she also recounts in her memoirs that you know probably very well, right? That when she was a postdoc at Princeton, she met Einstein. And one of the reasons why Einstein liked her work so much was exactly that it showed these properties of finite propagation and gravitational waves. So but that's another thing. I mean, she wrote memoirs, so that's another interesting book to read. Yeah, thank you all very much. And happy birthday again, Yvonne. So that was on the 29th of December, her 100th birthday. I think it's wonderful and an honor to be able to speak here. And thank you very much.
Thank you, Lydia. It was an awesome talk. Okay. Clapping, not hand raising again. Got it.
Sorry.
I think Miha.
Thanks a lot. Yeah, thank you.
I think Mihalis, I've made you co-host, so you should be able to unmute yourself and share your screen. We'll start in about 4 minutes.
Okay, I'll attempt that. Okay, can you indeed see my screen?
Yes.
Okay, let me just... okay.
Yeah, seems to work. Perhaps we should wait for the time to start in case more people want to join.
So Mihalis, you are now at Penn State, right? You arrived?
That's correct. So I'll see you hopefully very soon.
Yeah, we'll see you very soon. Wonderful.
I'm arrived.
I just
Yes.
wanted to make sure that you are in town. Great. Okay. See you soon.
We heard that
Thank
you had a
you.
storm
Thank you,
lately,
Mihalis.
Michalis, at Penn State.
Sorry?
We heard that you had a blackout earlier on, so we are happy to have you back on.
Okay, I see. I didn't realize that maybe, but it's been very windy, sort of since yesterday. So
Yeah,
I guess.
yeah. We lost power for in the middle of the night.
Oh, I see.
So
I see.
I was quite concerned. I thought I had to go to do something. I didn't know what, but luckily power came back. So,
Well, the weather was, I mean, the drive over here from Princeton was, I mean, I got some weather on the way. So
a little bit of adventure, yeah.
Thanks so much for accepting and giving this talk today from the organizers. Just want to thank you for that.
it's a pleasure to participate in this. It's really a very nice event.
All the talks that you may not have been able to watch are on the YouTube channel, so
I've already, in fact, seen some, that I couldn't watch live because of the time difference. I've already actually been watching the YouTube, so I think many
okay.
people will be tuning into those. So it's great that you've
Okay.
put them up.
Thank you. Thanks. Good. Great.
Okay, Mihalis, should we start?
We can anytime.
Yeah, I mean, it's time. I'll just introduce you. So our final speaker for this conference is Mihalis de Formos from Princeton University and the University of Cambridge, who has driven through storms to actually be with you here today. So thank you. And he's going to tell us about extremal and near extremal black holes. Mihalis.
So thank you very much, Kartik, for the introduction. So let me just say at the onset that it's really an honor to be able to speak at such an occasion, celebrating 100 years of Yvonne Choquet-Bruhat. She is a towering figure in this field, a personal inspiration to me, but also everything that I'm going to talk about, in some sense, stems from a framework namely the framework of understanding nonlinear dynamics in general relativity that really was created in her 1952 work. But some of her more recent work will also, in some sense, be relevant, and I'll try to remember to make specific reference to that also. Okay, so let me begin my talk. My talk is titled Extremal and Near Extremal Black Holes. So let me immediately tell you the plan of my lecture. So first I'm going to very quickly review what I'll call the sub-extremal black hole stability story. So we heard a very nice talk by Elena Georgi earlier in this conference. So I'll actually be able to be rather quick. And then I'll pass to the subject proper of this talk, which is really about extremality. And as a little sort of spoiler alert, somehow the thesis of this talk is that most of the discussion about extremality, extremal black holes and general relativity, has been overshadowed by two dominant paradigms. And the thesis of this talk is that these paradigms are not correct, and somehow understanding that brings us all already halfway to what are the correct questions to ask about extremality. So in particular, I'll pass to a stability conjecture for extremal black holes, question mark. And then at the very end, I'll talk about something very, very recent, Kayla Unger's extremal critical collapse and a new picture of phase space. Okay, so this is my plan. So let me jump right in with the sub-extremal stability story. And so, okay, just so that we're all on the same page. So we all know the Kerr family spacetimes found by Roy Kerr in 1963. So this is the famous Kerr metric. So of course, this is a two-parameter family of stationary axisymmetric solutions of the vacuum equations, the parameters being the rotation parameter, and m, the mass. And this, of course, as we all know, describes black hole spacetime if the parameters satisfy modulus of A less than equal to m. So, of course, we have the special cases that we know and love. So A equals 0 is the Schwarzschild case. Modulus of A strictly less than m is the so-called sub-extremal case. And finally, A equals m is the extremal case. So is this actually full screen, by the way? Because if it's not, I can...
No, it is not. Yeah.
Okay, I will enter full screen. Okay, so this will be better. Okay. So I hope this is better then. Okay. So just to recall that the extremal case means that the so-called surface gravity, which is traditionally denoted by kappa, is equal to 0. Okay, so this is the Kerr family. So to talk about and maybe I should say that, of course, black hole spacetime corresponds to the case where the modulus of A is less than or equal to m, and as is well known, if the modulus of A is strictly bigger than m, then this family has a so-called naked singularity, which is a cause of a lot of confusion in the literature, to which I'll refer later on in the talk. Okay, so what about stability? So the first nonlinear stability result in this subject without symmetry was the full nonlinear stability of the Schwarzschild family. So this is a result from a few years back, joined with Holzegel, Rodniansky, and Taylor. And I'll actually return to the precise statement of this result much later in the talk, because this will be very important as a model for understanding what we should ask about extremality. But let me just say informally that the statement of the theorem is that the Schwarzschild family is indeed asymptotically stable in the exterior as a solution to the Cauchy problem for the Einstein vacuum equations, with no symmetry assumptions for the full expected set of perturbations. And again, just to give a brief spoiler, why do I say for the full expected set of perturbations? Well, we all know that Schwarzschild sits inside the Kerr family. So in particular, you can just perturb into the Kerr family. And if you perturb into the Kerr family, then you will not asymptote back to Schwarzschild. So you only actually expect that you are stable to a finite codimensional set of perturbations, which basically kills the Kerr family. And this is precisely the statement. Okay. So in particular, this theorem characterizes all perturbations which asymptote back to Schwarzschild. Okay. So let me just say a few words about this result. And again, as I said, if the statement is at all confusing, we will return and I will give you actually the precise statement of this theorem later in the talk. But let me just say some previous work. Of course, the study of stability of black holes goes back to my academic grandfather, Johnny Wheeler, and Reggie in 1957. So they had the first results pertaining to stability of Schwarzschild. This was the mode stability. But one particular result that I want to highlight was the full linear stability of Schwarzschild, which was obtained with Holzhegel and Rudniansky in 2016. And somehow the main difficulty in this business was actually understanding the full linear stability. That's to say, the big delay in understanding nonlinear stability results in this business is not actually coming from any nonlinear issue. It's coming from incomplete understanding of the linear theory. And even though the study of linear perturbations on Schwarzschild is a very classical problem, it was the incomplete understanding of the linear theory which caused sort of the big delay in understanding anything nonlinear. Okay, so there are many other sort of previous work that is listed here, and I won't really discuss in detail. Elena, of course, in her talk, discussed some of this work in more detail. So let me just give my own sort of takeaway lessons from the proof of this theorem. So as I just said, nonlinear stability is fundamentally a linear problem. And there are two ways of looking at that. So somehow what that means is that if one actually understands well enough the linear stability, then one can hope to indeed prove nonlinear stability using standard tools in nonlinear analysis developed over the last century. So there are two ways of looking at that. One, depending if you're sort of the positive and the negative way. So what this means is that, well, if with your linear stability, you cannot prove a nonlinear stability statement, then you haven't actually understood completely linear stability. That's sort of the negative way. But the positive way is that if indeed you understand linear stability, you can indeed complete a nonlinear stability proof. So this is somehow the fundamental thing. But of course, there's a big but. And the big but is that well, first of all, you need a true linear stability result. So in particular, you need not just some sort of soft statement that linear gauge invariant, let's say, quantities decay, but you need something much more quantitative. You need to know that gauge invariant quantities decay sufficiently fast. And of course, the reason for this is that if you have any hope in understanding the nonlinear theory, you have to somehow put back this decay into the nonlinear equations, and it has to integrate up. So this is something very important. In fact, this fact is in some sense what distinguishes this problem in the asymptotically flat case with the analogous problem, let's say, in the asymptotically anti-de Sitter case, where you have some versions of linear stability, but you have very slow decay. And this means that the question of nonlinear stability or instability is a truly nonlinear problem. Okay? But moreover, it's not actually enough to have sort of sufficiently fast decay. But you also, I mean, there's a particular threshold that you have to sort of pass. And in order to pass this threshold, you have to actually understand some very well-known, again, qualitative features of black hole geometry, namely the effect of trapped null geodesics. These give rise to sort of concentration phenomenon of waves, and you have to quantify this. Particularly, it's very important that you understand the instability of trapped null geodesics, the instability of photon orbits. You also have to quantify and understand the redshift effect, which of course is related so the local redshift effect at the horizon with the positivity of surface gravity. So there's this aspect of the problem. So this really is saying that you really need a complete linear stability statement. But moreover, and I also want to emphasize this point, it's not enough to just have linear stability for the gauge invariant quantities, but you need a linear stability statement for the full statement for the full system in a well-posed gauge. And so you might say, well, why is this necessary? Sort of isn't, why not just deal with gauge invariant quantities? And the point is that, of course, in pure linear theory, the gauge invariant quantities exactly decouple. So you can prove something about gauge invariant quantities and declare victory. But there's unfortunately no way to write the nonlinear theory purely in terms of gauge invariant quantities. There's always a weak coupling. And so you really do need also to say something about the non-gauge invariant quantities. I know it does. Abhay, do you have a question?
Yeah, quick question actually.
Oh, yes.
I mean, this is very beautiful, but also very thought-provoking, right? So yes, I mean, so if I look at just the Minkowski space stability,
Yes.
where I don't have these problems about the trapping of the null geodesics,
Yes.
etc., etc.
Yes.
But there we knew non-linear stability, linear stability for a long time. Or
yes,
I think we knew that very long time. But maybe you disagree. I don't know. So, are you saying that in that case, in fact, the non-linear stability was not such a big deal? That because after all,
well, that's
we had
no. So this is maybe related to a point that's coming up. So, but it's a very good I will address your question.
Thank you.
So the third issue is that the nonlinear terms have to be cooperative, and the point is that, of course, there is a subtlety about this. The subtlety is actually something purely at null infinity. This sort of this aspect of the problem. It's very related to things that Lydia talked about in her talk just now. It's very related to sort of subtleties about the asymptotic quantities and their behavior at null infinity. But in some sense, that problem was completely resolved in the context of the proof of the stability of Minkowski space. So if you want, the only genuinely non-linear issue in these problems is an issue which is already present and resolved in the context of the nonlinear stability of Minkowski space. So yes, I'm somehow incorporating that lesson in this discussion, but sort of modulo that, and of course that was highly non-trivial when it was first understood. Now, of course, there are much more efficient ways of understanding that, so sort of it's much less of a difficulty than it appeared psychologically and technically at the time. But there is a sense in which that's something that really just has to do with null infinity and does not have to does not really interact with the other aspects of the problem. So I hope that
yes, thank you.
Answers that. Yes. And okay, this maybe I'll also add this, that of course there are many other technical issues in implementing a nonlinear stability proof. And one of the big challenges in this subject is to find ways of doing this efficiently so that the proofs are short and comprehensible. Okay, so that's already about Schwarzschild. So let me just say very briefly about when you perturb Schwarzschild ever so slightly. So in particular, the case of very, very slowly rotating Kerr. So the underlying linear theory for this was unlocked in two independent works, actually a work of mine with Holzigel and Rodniansky, and an independent work of Ma, which was also based on some of our previous work in the Schwarzschild case. And since then, there have been works by various people. So works by Anderson, Bechdel, Blue, Ma, Hefner, Hinz, Fassi on the full linear theory, and also some recent papers of Kleinerman, Scheftel, Shen, Kleinerman, Scheftel, Georgi, that we heard a little bit about in Elena's talk. But maybe the most interesting thing in the subextremal story is truly the Kerr solution, the actual Kerr solution when you're not very, very close to Schwarzschild and you cannot base things on a perturbation of Schwarzschild. And here, I think, is where the most interesting things in this story have happened. And so this is the work of Jakob Schleppentoch-Rothman and Rita Teixeira da Costa. So they unlocked the linear theory in the full subextremal case in this beautiful set of papers. And in particular, just so that it's clear that there's a new physical thing that has to be understood. So of course, the big difficulty in Kerr, as opposed to Schwarzschild, is actually the problem of superradiance. This is really the big difficulty. There are many superficial difficulties, but the true difficulty is the problem of superradiance. And in reality, in the very slowly rotating case, superradiance is not such a big problem because it's governed by a very small parameter, and you can essentially absorb that in the argument. So it's really only in the subextremal case where you have to face this actual physical problem. And so one question is, well, what governs the strength of superradiant amplification? How big can superradiant amplification be? And even though this is fundamentally an ODE question, it's really about an infinite set of ODEs if you're really interested in bounding superradiance over all frequencies, which is what you have to do if you want to fully understand the linear problem. So in particular, a corollary of these statements is that superradiant amplification can be bounded by distance from extremality. So if you give me a distance from extremality, then there is some bound that could degenerate as you approach extremality, and we'll get to that later on, that bounds superradiant amplification. And this is a highly non-trivial thing, and they sort of use all the structure in the Tucholsky system and the relevant Starobinsky-Tucholsky identities in order to understand this. Okay, so anyway, this I think is maybe the most interesting thing that has happened as far as a black hole stability in the subextremal case in the last few years. Okay, all right, but of course, so in particular, in view of this and in view of the general comments that I made, I think one can hope that a write-up of a complete proof of the nonlinear stability in the full subextremal range can be done in the near future. Okay, all right. So that's great, but of course, the subject of my talk is actually about extremality. And as I advertised at the beginning, the whole discussion of extremality has been overshadowed by what I'll call two dominant paradigms. So what are these dominant paradigms? So the first paradigm that I want to discuss is what I'll call the third law paradigm. So this originates in this very celebrated paper of Bardeen, Carter, and Hawking, the 4 laws of black hole mechanics. And here sort of we read from the abstract of the paper, expressions are derived for the mass of a stationary axisymmetric solution of the Einstein equations containing a black hole surrounded by matter, and for the difference in mass between 2 neighboring such solutions. 2 of the quantities which appear in these expressions, namely the area of the event horizon and the surface gravity, kappa that I showed you before, of the black hole, have a close analogy with entropy and temperature, respectively. This analogy suggests the formulation of 4 laws of black hole mechanics, which correspond to and in some ways transcend the 4 laws of thermodynamics. So this is the abstract of this famous paper. And you see, in particular, kappa, the surface gravity, the quantity which is 0 in the extremal case. This is the quantity that should have an analogy with temperature. So in the spirit then of this analogy, this paper introduces the third law of black hole thermodynamics, which is the statement that it is impossible by any procedure, no matter how idealized, to reduce kappa, the surface gravity, to 0 by a finite sequence of operations. And this law was later refined further in an influential paper of Werner Israel. And somehow if you want to way to think about this paradigm is that you should think of extremal black holes as some physically inaccessible ideal limit. Okay? This is somehow the paradigm. Okay, so before introducing the other paradigm, it's somehow the other paradigm that sort of, if you want, clouded the discussion of extremal black holes. Let me give another quote from the paper we just saw of Bardeen, Carter, and Hawking. So another reason for believing the third law is that if one could reduce kappa to 0 by a finite sequence of operations, then presumably one could carry the process further. thereby creating a naked singularity. Remember that in the Kerr case, if the modulus of A is strictly bigger than M, then the Kerr solution contains, as we well know, a naked singularity. If this were to happen, then there would be a breakdown of the assumption of asymptotic predictability, which is the basis of many results in black hole theory, including the law that A cannot decrease, etc., etc. Okay, so somehow another justification for hoping for this third law is, well, if you could make an extremal black hole, then why can't you make a naked singularity? So this brings us to the other paradigm, which is the overspinning supercharging paradigm. So the, in some sense, unwilling godfather of this paradigm, and unwilling because, well, for reasons that you'll see in just a second, is Bob Wald. So he wrote this very influential paper, Gedanken Experiments to Destroy a Black Hole. And in this paper, he entertains this notion that, well, maybe indeed you can try to create naked singularities by throwing in a charge or throwing in some sort of rotation to a extremal, well, Reisner-Nordstrom, the charged case, or Kerr in the vacuum case black hole. But of course, and this is why I said unwilling, the point of his paper is that at least in the test particle approximation, you cannot do that. Okay? So in some sense, Bob Wald in reality showed that you cannot overspin supercharged black holes at least in a certain approximation that he worked in. But nonetheless, this paper gave rise to a vast amount of subsequent literature of people trying to, find various ways to overspin or supercharge black holes. So this sort of paradigm, if you want, is that extremal black holes are a possible gateway to a naked singularity, and we should study them either, in order to show that we can create naked singularities somehow starting from extremal black holes, or well, as Bob Wald do, we should show that this is somehow not possible because the third law is true, because you couldn't have an extremal black hole. Okay. So this is just a quote from the paper, just to confirm the fact that in his actual paper he was not he was not actually advocating that you can overspin or supercharge black holes. In fact, the conclusion of the paper was very much the opposite. But nonetheless, the paper has given rise to a huge literature of that type. Okay, so what is the status of this? Why do I say that these paradigms are something we have to get over? So first of all, the third law is actually false, plain and simple. So this is a theorem of about a year ago of Kayla and Ryan Unger. Actually, I think Piotr Kruszal mentioned this result at the very end of his talk. So the theorem is here's the sort of snippet from the actual paper. So sub-extremal black holes can become extremal in finite time, evolving from completely regular initial data. And in fact, the easiest way to implement this is in spherical symmetry. So when you look at extremal charged black holes. So in particular, there exists regular one-ended Cauchy data for the Einstein-Maxwell charge scalar field system, which is an impeccable system, which is often used as a model in gravitational collapse if you want to model things in spherical symmetry. So there's regular initial data. In fact, the initial data can have a regular center. So we're really looking at gravitational collapse. So everything is sort of starting from a completely impeccable regular initial data with a center, the data completely in the past, the future, null infinity. And what can happen is that, well, you have gravitational collapse, and for early advanced time, for instance, you can in fact arrange that your your spacetime is exactly a Schwarzschild. So there's some region here where the spacetime is exactly Schwarzschild. So in particular, it's subextremal, doesn't get more subextremal than Schwarzschild. And then at some later advanced time and thereafter, it's exactly isometric to extremal Reisner. Okay? So you can, in finite advanced time, make a subextremal black hole. In fact, a subextremal black hole that has arisen even in gravitational collapse, you can make it exactly extremal. Okay, so that's their theorem, and the conclusion of the theorem is that whatever the third law was supposed to be, it's false. Okay, but I claim to you that the supercharging paradigm is also false. But to understand this, we have to understand better the dynamics in the neighborhood of extremal black holes. So this is what I'll turn to now. So the next topic is the stability conjecture for extremal black holes. And for this, it's useful to go back to Schwarzschild and to go back to the first theorem that I began the talk with, namely my theorem with Holzigel, Rodniansky, and Taylor about the full nonlinear asymptotic stability of Schwarzschild without symmetry. And I'll tell you exactly what is the statement. So the statement's the following. So first of all, again, due to very general results that, of course, when they were first proven were very difficult, but now they've been absorbed by the community. In trying to understand, let's say, the stability of Schwarzschild, you can go directly to characteristic initial data. That's to say, we know very well how to go from Cauchy data on a, let's say, asymptotically flat hypersurface to data on two characteristic future-going hypersurfaces. So imagine the problem starting from data on what I'll call C bar in and C out, which are two characteristic hypersurfaces, let's say in Schwarzschild, which are depicted in this Penrose diagram, where the C in penetrates the Schwarzschild event horizon, and you go a little bit further and you stop there. Okay, and the C out is an outgoing hypersurface that goes out to future null infinity, described less. Okay, so of course, Schwarzschild is a particular solution that arises from particular initial data. So the statement of the theorem is the following. Okay, look at the moduli space of all characteristic initial data on this C in and C out in a neighborhood of Schwarzschild. Okay, so this is an infinite dimensional space. We're looking at the moduli space of all vacuum initial data, okay, in a neighborhood of this particular Schwarzschild initial data. So there exists in the moduli space a codimensional 3 submanifold. So this is what I call M substable. Okay, so it's codimension 3 in the infinite dimensional moduli space with the following properties. If your data lie on that submanifold, then first of all, the evolution, so this notion, the maximal Cauchy development, the notion that Yvonne Choquet-Brab bequeathed to us. So the maximal Cauchy development of this data lying on this codimension 3 submanifold will have all the properties of Schwarzschild. That's to say, first of all, it will possess a complete future null infinity, complete scry, such that if you look at the past of future null infinity, the past will be bounded to the future by an event horizon. The event horizon will be affine complete null hypersurface. Moreover, everywhere in the domain of outer communications, the spacetime will remain close to the Schwarzschild metric that you perturbed. But finally, okay, and this is where the restriction to the codimension 3 submanifold is so fundamental, the spacetime will asymptote back inverse polynomially to another nearby Schwarzschild metric. Okay, and in fact, the claim is that this is an if and only if. That's to say, if you do not lie on this codimension 3 submanifold, then you will not asymptote back to a Schwarzschild metric. You'll presumably asymptote to a curve. So this is the full nonlinear asymptotic stability of Schwarzschild without symmetry, it characterizes exactly the full set of moduli space near Schwarzschild that asymptotes back to the Schwarzschild metric, and it says that it has exactly the codimension that you think it should have, which is 3. Now, let me just make a comment. So you might say, why is it 3 and not 1? Because after all, the Kerr family is a 2-parameter family. Schwarzschild is a 1-parameter subfamily. So you might think that the codimension of the moduli space that should asymptote to Schwarzschild should be codimension 1. Well, this has to do with a certain subtlety that Schwarzschild is more symmetric than Kerr. So you somehow, when you look at the linear theory around Schwarzschild, you see the same Kerr solution in many, many different ways, because of somehow you also have to keep track of the direction of the axis. Okay, so this computation is actually coming from linear theory. This is exactly the analogous sort of statement in linear theory, and you should think that morally you should think of this as being codimension 1, but actually because of this well-known phenomenon, when you linearize the equations around a more symmetric solution, it corresponds to 3. Okay, so could a similar statement hold for extremal black holes? That's the question. Let's just say, could a similar, codimension, let's say 1 statement hold for stability for extremal black holes? Okay, so there's a little problem if you hope for that to be the case, because there is a known instability in the extremal case, which is the celebrated Aretakis instability. So what's known, and in fact, you already see this in the simplest possible model for linearization. That's to say, when you fix, let's say, even just extremal Rice or Nordstrom, but more generally, any black hole with 0 surface gravity, and you look at linear waves on such backgrounds, then what Aretakis showed is that there are some first-order quantities involving the first derivatives of the linear waves, which are conserved on the event horizon. So in particular, they don't decay. And then if you pass to second-order quantities, so certain second derivatives of your linear wave, then there are certain specific, again, translation invariant combinations which actually grow. They grow polynomially. So on the horizon itself, there is some sort of instability. There are things that are growing. So okay, whatever is true has to sort of incorporate that. Now, despite this sort of instability, there are weak stability statements that you can make, and in particular, in the case of extremal Rice or Nordstrom, we have now sort of full weak stability results for gauge invariant quantities. So what do I mean by weak stability? I mean, okay, there is this bad phenomenon exactly on the horizon, but suppose we're not exactly on the horizon. Suppose we're just outside the horizon, so in the exterior of the black hole. Then we have indeed boundedness and decay results for all quantities for arbitrary high derivatives. Of course, the estimates have to somehow degenerate as you approach the horizon, but you can still sort of show some sort of weak stability. So this is actually a relatively recent result of Marios Apetroaie, who was a student of Aretakis. So you can see the full statement of his theorem here, but the details of the statement are not so important in the context of this talk. What's important to remember is that despite the instability, you still have stability of some quantities. So okay, that's great. Unfortunately, if you look at extremal Kerr as opposed to extremal Rice or Nordstrom, the situation gets worse. So it was recently shown by Gauge that actually, if you look at higher azimuthal modes, then there are worse instabilities than the Aretakis instability. That's to say, you actually have growth already of first order quantities, not just second order quantities. And embarrassingly, if you want a sort of an open, elementary open problem in this field, we still don't have any sort of understanding, any sort of weak stability statement, even for the scalar wave equation on extremal Kerr without restriction to axis symmetry. So in particular, it remains an open problem. Let's say you're far away from the black hole and you study the scalar wave equation on extremal Kerr. Does the solution remain uniformly bounded for all time? This is the weakest possible sort of stability statement that you could possibly make. This is open. So the only statement which is known outside of axis symmetry is so-called mode stability, and this is actually a recent statement of Rita Teixeira da Costa. Okay. So if you want or any students in the audience and you want, a very well defined, seemingly very elementary question, which is the answer to which is unknown, and I sort of I don't know what the answer to this question is. The question is, do solutions of just the scalar wave equation remain bounded in the exterior of subextremal Kerr? So again, in the axisymmetric case, this is understood. So the question is for general solutions. So this sort of goes to show how even basic questions in linear theory in the extremal case are still unknown. Okay, so so that's very good. Nonetheless, it's important to be brave despite the unknown and be willing to make conjectures. So indeed, in my paper with Holzigel, Rodniansky, and Taylor, where we proved the nonlinear stability of Schwarzschild without symmetry, we made a conjecture for extremal black holes of a similar type. Actually, we were brave, but maybe we were not brave enough in that exactly because of this situation that I just described, namely exactly because there are weak stability results known in the extremal Reiser-Nordström case. In the Kerr case, clearly the situation is worse, and we don't even have weak stability results apart from Rita Teixeira da Costa's mode stability. We chickened out of actually committing to a conjecture about extremal Kerr. We only made a conjecture about extremal Reiser-Nordström. But, this being a more physics audience, I'm very comfortable with being more brave for the purpose of this talk. So let me change my conjecture so as to apply to extremal Kerr, partly because this way I don't have to talk about some sort of subtleties of codimension counting in the extremal Reiser-Nordström case. So in fact, I should say that we said in our paper that you could make this conjecture for extremal Kerr, but we sort of refused to commit to it. But okay, let me use the benefits of technology to a posteriori modify the conjecture to refer to extremal Kerr, and this will at the very least make it slightly easier to talk about. So what's the conjecture? So the conjecture is in complete analogy with what we proved for Schwarzschild. Namely, think about extremal Kerr. So this is, if you want, the Penrose diagram. So think about extremal Kerr as arising from characteristic initial data on C in and C out. And again, it's important to remember that for C in, we have a finite ingoing null hypersurface, and we stop at some point after we've crossed the event horizon, and C out goes to future null infinity. So we are only looking at evolution in the domain of dependence of this bifurcate null hypersurface. So again, you can think of exact extremal Kerr as a solution that arises from specific initial data, namely extremal Kerr initial data. And so the statement is the following. Now look at the moduli space of all initial data in a neighborhood of this extremal Kerr initial data. Then there exists a codimension 1 hypersurface passing through extremal Kerr initial data with a property that if you're on that codimension 1 hypersurface, then the solution will evolve back to a nearby extremal Kerr solution. Okay? But, of course, since we believe in the Aretakis instability and possibly these worse instabilities of gauge, then the generic element of this codimension 1 submanifold, so the generic initial data on M stable, okay, will suffer on the event horizon from the Aretakis instability. That's to say, certain quantities along the event horizon, certain higher order quantities will grow polynomially. Nonetheless, the metric itself will asymptote to extremal Kerr. So that, if you want, is sort of the full codimension 1 asymptotic stability of extremal Kerr, but with horizon growing hair generic. So this is the natural conjecture if you're an optimist that you would infer from the kinds of statements that have recently been obtained in the literature. Okay. So again, because we're in the business of believing conjectures for the purpose of this talk and sort of going forward, so let's say that we do believe this conjecture. So let's believe that indeed there exists this codimension 1 submanifold of moduli space passing through extremal Kerr. And remember, we're always here talking about the moduli space of solutions arising from this kind of characteristic initial data. Then what does this submanifold separate? Because you might think if this is a codimension 1 submanifold in moduli space, it should be separating 2 regions. So what are these 2 regions that it's separating? So again, we write in our paper, moreover, one could hope to prove that this submanifold M stable delimits the boundary signifying a phase transition between 2 very different open regions of moduli space. Namely, the set of data leading to spacetimes failing to collapse in the time allotted. So remember, failing to collapse in the time allotted, I have only finite, initially, I only have finite retarded time available to me. Okay, so failing to collapse in the time allotted simply means that the evolution of this initial data goes all the way to future null infinity for all retarded time allotted. Okay, the total retarded time here would be finite, but okay, I've ran out of data, so I don't know how to continue. Okay, so that set and the set of data leading to a black hole exterior settling down to a sub-extremal Kerr. So let me draw a little picture of this moduli space. So again, this is just moduli space of solutions arising from this kind of initial data. So the picture is we have this codimension 1 submanifold M stable, and it separates spacetimes collapsing to sub-extremal black holes. So spacetimes for which somewhere here there's a horizon. I hope you can see my cursor. So somewhere here there's a horizon, and the spacetime asymptotes to a sub-extremal black hole, and spacetimes that fail to collapse in the domain of dependence. So spacetimes for which null infinity goes all the way up to here, the total retarded time is finite. So the spacetime can be extended further, but we've ran out of data, so we can't discuss the extension because, okay, we're not parameterizing that in the modulus. Okay. All right. So one thing I want to point out is that a sufficient condition to lie on the right-hand side of this diagram, that's to say here, is the presence of a single trapped or marginally trapped surface. So if there happens to be in my initial delta a marginally trapped surface, then I necessarily will lie actually on this side. So in particular, this completely would tell you what happens if I start with an extremal black hole and I try to do something with a small perturbation. Okay? And this will say that, well, the only thing that can happen is either I'll collapse to a sub-extremal black hole, I'll collapse to an extremal black hole if I'm fine-tuned to be on this codimension 1 hypersurface, or I'll fail to collapse in the time allotted. So in particular, let me point out that this would imply this conjecture that overspinning supercharging paradigm is definitively false, because all those considerations refer to the domain of dependence of such hypersurfaces, all of those considerations, if you think about them. And what this is telling you is that whatever happens, that's to say, wherever you lie in this picture, okay, there are no naked singularities. There are no, everything is completely stable in some sense. Okay, so there's nothing of the form that is being talked about in those papers. So that, in particular, closes the book on that discussion. Okay, so
what happens to the instabilities that are growing? I mean, on the right hand side picture, when it is actually just sub-extremal, but still the Aretakis and the Gaich instabilities are going to grow on the horizon, right?
So that's a good question. That obviously that somehow quantitatively, if you're at some distance from this stable submanifold, if we believe that this is the picture, then in some transient era, you will see those instabilities again. So one thing that means is that you cannot show, you cannot really hope to show stability in this context without some understanding of how to deal with this sort of transient era. Okay. So yes, indeed, you will see those phenomena, and you can in fact very softly argue that just by Cauchy stability type considerations, you will see that. Yeah.
But then we should see such phenomena just in the context of sub-extremal black hole, right?
Yes.
So, but do we see that in the sub-extremal black holes where we look at the stability?
Yes. Well, near extremality, you will see that at a for a transient era.
Yeah. Okay.
I mean, somehow what it means is the following: that somehow, you see, what you can hope to understand. So I said earlier in my talk that in principle, one can hope on the basis of the progress in linear theory to write up a full nonlinear stability for the sub-extremal case. But what you should think is that actually what that would mean, if you don't want to understand quantitatively the extremal case, is that you'd actually be, understanding a picture of moduli space which came out like this. I don't know if you see my cursor.
Yeah. Yep.
Which sort of, the closer you get to extremality, the smaller the perturbation had to be in order to sort of understand the. So somehow, to be able to, let's say, understand perturbations of even sub-extremal Kerr, but where the size of perturbation doesn't care about the distance to extremality, you would have to understand this picture essentially that I'm drawing. So in particular, if you want to understand that, you'd really have to understand the extremal case. So what you can hope to understand without true understanding of the extremal case is really, the closer I am to extremality, the smaller I make the perturbation.
Right.
So just a clarification just there. So this Unger and I don't know the other name, but the result that the third law is false
Yes.
Because there again, you're sort of going from the sub-extremal black hole to the extremal. Yes. So where does that picture, I mean, can you give a picture of that in this picture that you have? Because there as well, you're going from sub-extremality, presumably, to extremality in some way.
Yeah, so this picture, I should say, is compatible with that, because of course this is I should emphasize, this is, these pictures of moduli space are teleological. What do I mean is that you can think that the moduli space is parameterized by initial data. That's what Yvonne Choquet-Brouat taught us, that we can parameterize solutions by initial data. But where you land in this picture is something that you have to evolve for all time to know. So in particular, you could start with something which is very close to sub-extremal, and you could land on this red hypersurface. So a third law violating solution would be a solution of that type.
Right. Okay. Thank you. Yeah.
Okay. So one thing, of course, which is unsatisfying about this picture that I just drew is that it really, okay, this is a picture that completely understands the evolution of initial data that looks like this, but of course the initial data itself is not complete, exactly because I'm only looking at this finite ingoing hypersurface, which is, I'm stopping here, and it's exactly for this reason, okay, that although, okay, in some sense we know what happens to everything on the right part of this diagram, okay, that's to say, what if you happen to land on the right of this diagram, then we know that, okay, at least from the point of view of outside observers, we understand things for all retarded time. If you land on the left-hand side of the diagram, what this is really telling you is that to know what happens, we need to know how to complete the data, because we run out of retarded time. Okay, so what do these considerations actually say about let's say the initial data of gravitational collapse? Okay, so of course in this context there's a very influential picture that has developed and is very nicely surveyed in this paper of Gundlach and Martin Garcia, Critical Phenomenon in Gravitational Collapse. So let me show you a little picture which is often drawn and is taken from their paper. So they imagine the phase space of gravitational collapse as structured as follows. So of course you have trivial initial data, Euclidean sort of initial data that gives rise to Minkowski space. So this you can think of this as sort of what's denoted here, flat space fixed point. So we know that, of course, Minkowski space is stable. This is the theorem of Christodoulou and Kleinerman. So in particular, if you have data which is very close to trivial initial data, then we know it will disperse. It will disperse back to Minkowski space. On the other hand, you can have large initial data that collapses to form a black hole. So of course, this goes back in some context to Oppenheimer-Snyder, but you can also do it for Einstein's scalar field. You can also do it for the Einstein vacuum equations without any symmetry if your data is large enough. So you have the sort of dispersing solutions, you have the black hole forming solutions, and what's imagined is, well, let's take a one-parameter family of initial data that interpolates between, let's say, Minkowski space and some your favorite black hole forming solution. Then well, there should be a critical sort of solution on that family. That's to say, a solution that does not form a black hole. Well, this sort of threshold was studied quite a bit by Choptuik numerically, and it is thought that those critical solutions are naked singularities. Okay, and it's thought precisely that you can think of this as a codimension 1 hypersurface in the moduli space of solutions. So let me draw my own picture of this. So my own picture of this in sort of relation to the picture that I draw previously is as follows. So I'm really drawing the moduli space of, if you want, gravitational collapse initial data. So this is really the moduli space of all asymptotically flat one-ended Cauchy data that initially is completely in the domain of outer communications. Okay, and so of course data Euclidean space, so trivial initial data is living there. So we have Minkowski space arising from that trivial initial data, and we know that there's some set containing Minkowski space of dispersive spacetimes, of spacetimes that disperse. On the other hand, we know that there are spacetimes that collapse to black holes, and so the picture that we just saw in the other slide, redrawn in my picture, is, well, you imagine you have a 1-parameter interpolating family, and somehow the first solution that doesn't disperse, if you think about it coming this way, you expect to be a naked singularity, and there's all this literature on sort of universal phenomena associated to such naked singularities, etc., which maybe I don't want to say more. So, so this is sort of the traditional picture, but very recently, and this is really maybe 2 weeks ago on the archive, there was a paper of Kahle and Unger that followed up on their disproof of the third law, and what they show is that extremal black holes also can be thought of as critical solutions on the threshold of gravitational collapse. So their theorem actually involves the Einstein-Maxwell charged Vlasov system. And I promised I'd say, again, I'd give a reference to some of Yvonne's later work. So Yvonne Choquet-Brouillard really also initiated the rigorous study of the Einstein-Vlasov system in general relativity. And it's a very, very useful Mather model for proving theorems. So I really want to advertise both her early work on that model and this very recent work. So what they showed is there exist 1-parameter families of initial data for this impeccable Mather model. Everything is completely smooth, which interpolate between collapse and dispersion to a subextremal black hole. So you have a 1-parameter family of solutions that arise from completely impeccable, smooth, one-ended initial data, okay, that interpolates from Minkowski space and some initial data that form a subextremal black hole, where the critical solution is an extremal Reisser-Nordstrom, is a black hole that collapses to an extremal Reisser-Nordstrom solution, and to the right are dispersing spacetimes. So, and I will sort of end here. What this means is that we have to revisit this picture of the moduli space of gravitational collapse. And what's natural to conjecture in view of this result is that, well, okay, part of the boundary may be this codimension 1 boundary of critical naked singularities a la Choptuik, but there will also be another part of the boundary, which you might hope is again codimension 1, which correspond to critical extremal black holes. And you can think then this 1-parameter interpolating family constructed by Kahle and Unger would be a 1-parameter family which sort of crosses transversally to this boundary. So one thing I should say is that not all extremal black holes will be critical. So you can imagine that there are other branches of non-critical extremal black holes that schematically I can write like this. And if you think about the pictures of moduli space that I drew before, the sort of the partial moduli, the moduli space that concerned only the development of essentially what was partial Cauchy data, you should compare these two windows. So you see, in this window here, you can imagine that, on the right-hand side here, you had things that asymptoted to sub-extremal black holes. On the left-hand side, what you have here is things that did not asymptote to extremal black holes in the time allotted, but eventually asymptoted to sub-extremal black holes much later. So actually what's happening in this part of the picture is that there's a jump in the position of the event horizon as you cross sort of this threshold. Whereas what's happening in here is that there's a true transition between actually dispersing, not collapsing, and collapsing to a sub-extremal black hole. So you cannot distinguish these two things if I only give you partial Cauchy data. And both of these phenomena, I claim, are real phenomena. Okay? But the conjecture in view of this work of Cayley and Unger is that the moduli space should look like this. And in particular, there should exist extremal black holes at the boundary of the dispersive region. And well, if you believe this stability, then the set of these critical extreme black holes should be a codimension 1 submanifold of moduli space locally near this. So this is the picture. It's a hard picture to prove, I think, but I very much believe that this is the correct picture. So there's a lot to work on in the future. So with that, let me end my talk. Thank you very much for the opportunity to speak at this truly wonderful event in honor of Yvonne Choquet-Bruat.
Thank you, Mihalis, for the very nice talk. Are there any questions?
I have one question, which is one more question, which since nobody is raising their hand, I'm just jumping in. And that is that, we also think about, we've sort of learned to think about extremal black holes, and the slices looking with this throat geometry and the throat topology in particular. So I'm having a hard time thinking of sort of the non-extremal case and the extremal case sort of being continuously related to each other because of the spatial topologies being, in one case you have the throat that's infinitely far away. It has an infinite throat. Often in sort of loose terminology, it thinks of it as two different, as sort of very different topologically also, or more, I guess, explicitly geometrically. So to think of them as somehow continuously related, I'm having a hard time thinking about that. So I was wondering if you could give me a picture that would be useful. Thank you.
Yeah, so I've turned to this slide. So I think those issues coming from, if one focuses on this Cauchy hypersurface that goes from this point in the Penrose diagram to this, right? Because indeed, this is exactly that Cauchy hypersurface. But somehow, the point I'm trying to make is that dynamically, the relevance somehow, and as you said, in some sense, yes, that Cauchy hypersurface is, you're never going to see that Cauchy hypersurface if you don't start with, if you start with an asymptotically flat, sort of one-ended Cauchy hypersurface, then there can never be in the future a Cauchy hypersurface that looks like that. So, but the whole point is that, of course, but no one says that you cannot end up with a partial Cauchy hypersurface that looks like this. So somehow the relevant region of extremal black holes, and it's extremely, my whole point is that, and this does form, it does form fine. But the relevant region is the future of a Cauchy, of a partial Cauchy hypersurface that goes like this. That's somehow.
So yeah, I think can I interject a little bit, because I was also confused about this, but I think the pictures that we have normally about these extremal versus non-extremal are all in the stationary context, And as Mihalis has emphasized here, it's really a dynamical context, right? So on his first Cauchy hypersurface, it might look subextremal, but on this partial Cauchy hypersurface, it will be extremal. Is that correct, Mihalis? That's what you're saying?
And in some sense, I think, I don't know if I can actually write on this, but the first thing one has to do, if one wants to understand sort of, dynamical questions about extremality, the questions of the type that I phrase, because obviously, in other contexts, one might be interested in these t=0 slices, and that's perfectly fine. But if one's interested in dynamics of gravitational collapse in black holes, when thinking about extremal black holes, the first thing you should do is just get rid of all this. It's the first thing you should do, because this region is not relevant for the discussion. So what's relevant is exactly, what's in the future of this. So
I see.
Somehow,
so it's somehow
the first thing one should get rid of, because for the reason you said, that sort of, this part of the space-time near here, cannot arise dynamically.
right.
So if one's interest is in, let's say, the dynamics of black holes that actually form in gravitational collapse, that this part of the space-time cannot arise. But this part can, and it does, and that's what was proven. And many people didn't think that this could happen exactly because of, so I think it's actually just conceptually, in the context of gravitational collapse, when we think about extremal black holes, one has to somehow mentally erase this region. In particular, erase sort of this R=0 singularity also, because somehow, again, it is not relevant in the domain of dependence of this. So the domain of dependence of this initial data, does not see this R=0 singularity. It's not near it. And this is exactly why somehow all these attempts to conjure up an R=0 singularity by overspinning, overcharging, this is why they were doomed to failure. In some sense, you can already, if you just look at the Penrose diagram in this way, you can already see that it was very implausible that somehow, the R=0 singularity here should have anything to do with what happens if I perturb initial data there. But nonetheless, all that literature of supercharging, overspinning, that's what they were trying to do. I think in retrospect, it was quite implausible that sort of this would have anything to do with anything. But anyway, I think the correct picture to have for the purpose of dynamics of black holes is really to erase everything here. And so in particular, things that have to do with the throat, let's say, which is infinitely far away, which is purely a phenomenon about this region.
Right. So does that also kind of change our picture? I mean, so I understand what you're saying, that it's dynamically, and so the image we have of that extremal black hole, basically, so it's going to the point where A=m, but nevertheless, you don't have even at a late time, you don't have these slices which look like the classical slice from I0.
Yeah, exactly.
That's, I guess, the point that you're making. And so our image of what an extremal black hole, and it's no longer that kind of black hole. It's something which is extremal from the point of view of A=m. So thank you. That was really useful. Thanks.
Thanks.
So Mihalis, you pointed out that in your first picture that you had about the first conjecture, that you had this the part of the Cauchy data which was to the right, which then went to non-extremal black holes, right? And in that case, you said that the necessary sufficient condition there was that there was actually
unfortunately, I see that I've ruined my picture, but okay. Let's hope
you can erase it by going back. But
well, anyway. let's
Right,
ignore
that picture, right? Exactly. But as you said, that the necessary and sufficient condition that you're on the right hand side is that some of this initial data has a marginally trapped surface. Yeah, in fact, you said it here. The sufficient condition, not necessary,
right,
is the presence of a single trapped surface or marginally trapped surface.
Yeah.
So in the top diagram or in the space-time diagrams you draw, not the modular space diagram, but in the space-time diagram, where are these marginally trapped surfaces? Are they on the characteristic?
I'm just saying that. So for instance, okay, you look at this space. Okay.
Yeah.
You look at this space. So, well, there are lots of things that live in this space because, of course, I'm just looking at all initial data, which is some distance from the exact extremality. So, for instance, the exactly subextremal initial data, exactly subextremal Kerr initial data, will live, in this moduli space. And of course, okay, if you're exactly subextremal Kerr initial data, you know exactly what's going to happen. You're going to go to subextremal Kerr. Exactly super extremal Kerr lives in this data, of course, and you know exactly what's going to happen. Namely, you're going to run out of, you're going to run out of Bondi time. So it's going to be exactly, so exactly. So you can think that the exact Kerr data, intersects like this, and indeed the exact super extremal will be here, exact subextremal will be here. And of course, in the subextremal case, there will be on the initial data, there will be marginally trapped hypersurface. But okay, you also will have some, let's say, initial data that isn't exactly anything, but let's say still, because remember, this is, you should think we're looking at an open set of moduli space. And well, as you know very well, if you perturb, so if I have these things in the moduli space, if I perturb this ever so slightly, I certainly have a neighborhood of this. And of course, I know that, if I perturb this small enough, I'll still have a trapped surface. So that's an example of initial data that, just on the basis of the fact that there's a trapped surface, if you believe this picture, it then has to lie on the right-hand side and not on the left-hand side. But, there will also be initial data that don't have any trapped surfaces or marginally trapped surfaces initially, but nonetheless will end up on the right-hand side. And of course, that means that they will develop such
marginally trapped surface.
Such marginally trapped surfaces in evolution, but they won't necessarily. So this is why.
My question. There's very nice work by, I think his name is An, who is in Singapore now, the geometric analysis person who used to be in Princeton. Maybe I'm pronouncing the name wrong. Yeah, you're not. So there's very nice work about how these these marginally trapped surfaces will evolve in time and will make dynamical horizons. So does one know anything about these marginally trapped surfaces? Supposing I did have a marginally trapped surface on the initial data itself, does one know its trajectory to?
Well, what's interesting, and one thing, maybe I'll go to another picture here, because I'll go back to, and hopefully it will not obstruct here. So actually, one interesting thing that one sees, and this is very much related to this third law, is that so what's actually depicted here in black is a dynamical horizon in your terminology. Okay. And what you see is that the dynamical horizon actually there's a jump. Okay, so what's depicted, to be more precise, is an outermost, outermost in the null sense dynamical horizon. So another way to think about this is that the dynamical horizon has two connected components.
Okay.
And in fact, one thing that they proved, and this is also related to some mistakes in earlier literature about the third law, is that it's necessarily so when a subextremal black hole becomes extremal. that somehow for this to happen, there has to be a discontinuity in, or to say another way, there has to be several connected components. Because one can prove, in fact, that were this dynamical horizon connected, okay, you could disprove this picture. So the claim, and I think it's a very interesting point, is, you see, if you're safely in the subextremal region, okay, so let's go back to this picture here, okay. So if you're safely over here, then you definitely expect, and I think a theorem can be proven, that eventually there will be a perfectly smooth dynamical horizon, which eventually generically will be space-like, et cetera, and will have all the very nice properties that, whose study you've pioneered. What's interesting is that when you're very close here, when you're very close to this frontier, then there will be some nasty behavior, exactly
Great.
because somehow in the exact extremal case, then you could have situations where there are no trapped surfaces or marginally trapped surfaces. In fact, you can have situations where the horizon becomes exactly extremal and stays that way, in which case you can think of the horizon itself as a marginally trapped tube, but without trapped surfaces immediately on its inside. So so basically the let's say the behavior of dynamical horizons in a neighborhood of this frontier is interesting and different. But I mean, one expects to be able to prove with essentially with redshift estimates, which is actually what An, for instance, is using in his paper. So basically, using the positivity, if your surface gravity is safely positive, then you can prove very nice sort of statements about the eventual behavior of dynamical horizons.
Fantastic. Okay, I want to ask more, but I think we're meeting in 2 hours. So
we'll talk indeed. So.
I'll ask you that. Okay, thank you.
Indeed.
Thank you very much.
Are there any other questions for Mihalis? Okay, thank you, Mihalis, for the wonderful talk. That brings us to the end of this conference. So I want to thank all the speakers for the really great talks highlighting the great, wonderful work of Yvonne Choquet-Bruhat. The recordings from yesterday are already on YouTube, and today's recordings will be there shortly. So like, share, and subscribe. I think that's what I'm supposed to say. I also thank IAGRG, Raman Research Institute, and the International Center for Theoretical Sciences for helping us put all this together. My co-organizers, Shelab and Prayush, for doing amazing work putting all this together. Special thanks to Sumati Surya for completely spearheading the organization of this conference in honor of Yvonne Choquet-Bruhat. Thanks to the IT team at Raman Research Institute who put together all the Zoom machinery behind us, so this was possible. And finally, thanks to all the attendees for coming, joining us, no matter what time coordinate you're using. And through these talks, we've seen the vast influence of Yvonne Choquet-Bruhat's contributions. And I really hope that we and future generations of physicists and mathematicians continue to be inspired and build up on her ongoing with her amazing work. Thank you, everybody.
A request by Prayush to take a picture on Zoom. So let's do that. Let's everyone get their videos on. I'm not sure how to do it, Prayush. I'll leave it to you. I don't know how to take a picture. think you're sideways, Prayush. So okay. Prayush, you're sideways, so you'll have to get.
I'm not able to fix that, unfortunately.
So yeah,
That's going to be interesting. Yeah. All right. So maybe with whoever else. So do you know how to take a picture? Ah, there you are. Okay.
I think there's only one person who is not on camera, which is Mangala Hegde.
Yeah, that's Arun, our IT team person, who you should be on
Okay.
it as well, because he's been very instrumental in making sure that we had no glitches. So please, and Zadig also is. Mangala are not yet.
Mangala, could you switch on your video if you don't mind?
Okay, so we have at least a picture. So, okay, great, wonderful. So now you're back to being sideways. This is yeah. All right. So I think we can all take a picture now. Okay, who's taking the picture?
I took some screenshots.
Okay, great, excellent.
Okay, good.
So, have you taken one with Prayush properly oriented?
Yeah, I had taken all the orientations.
Okay, great. Thank you. So thanks so much, everybody. Thank you for being here, and it was absolutely delightful 2 days. And I think all of us had many more questions. Hopefully, we'll catch up and maybe also bug you with silly questions over time. Maybe that'll be the best compliment. But thank you very much for all your talks, and good night.
Good night.
Bye.
Thank you, everyone.
Good day, everyone.
Thank you so much.
Good night.
Bye, guys. Bye. Thanks a lot for all the work and effort. Thank you very much. I think this was a lot of fun for me. Bye.
Yeah, bye-bye.